Before I start, it is an unofficial school rule that all haircuts must be verbally acknowledged. So yes, I've had one of my haircuts for the year. I usually have 3 of them. Anyway, let's get on. This is video 16 of the GCSE Physics video series, all about space. Here we go. So it's been a long time to get here, but we are nearly at the end of the course. This is lesson 97, Formation of the Solar System. Now, part of this, you need to have the general knowledge that a lot of students acquire when they are much, much younger. Usually primary school age. They learn the order of the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There they are. Obviously, the picture on the left is not to scale, not even close. I think that the size of the bodies are to scale, but the spacing are not. And there is a lovely website that you can search for, something along the lines of tediously accurate model of the solar system where the moon is 1 pixel. If you just Google that, you'll find it. It's absolutely wonderful, where you can scroll across so that the speed of light is, well, it's scaled so that it scrolls at the speed of light on the scale that the image is. And it is as tedious as it is described. The solar system is mostly empty. But there we go. These are the planets, and we can separate them into 3 categories. It used to be 2, it's now 3 categories. You've got your rocky planets here, the terrestrial planets, the rocky planets: Mercury, Venus, Earth, and Mars. Venus being about the same size as Earth, Mercury and Mars being much smaller than the Earth. Mars and Earth, both of those being within what we would call the habitable zone. Mars only just, but Earth is solidly in the habitable zone, which is good because there's life on Earth. Jury's out about life on Mars. At the time of recording this, there is no evidence of life on Mars, but, you know, things change. Then what do? We go further out and we have our gas giants, Jupiter and Saturn. Saturn is notable for having those beautiful ring systems. And then we have our ice giants. They used to be counted as gas giants as well, but they're ice giants. They're about the same size as each other, Uranus and Neptune. If you want to have a hilarious laugh at the word Uranus, that's fine. It's... I mean, you're probably old enough to have got over the humour of it, but that's maybe not. Anyway, so here we have our 8 planets. There are also dwarf planets, such as Ceres, which is found between Mars and Jupiter in the asteroid belt. Often depictions of the asteroid belt make it look far more densely populated with asteroids than it actually is. It's very, very sparsely populated. Then you've got other dwarf planets like Makemake and Pluto, all the way out there as trans-Neptunian objects. Orbit of Pluto is, at times, about the same distance away from the Sun as Neptune is, so you can't really call Pluto a planet. There's some other things we need to define here. So in the centre of our solar system is a star, but before there was a star, there was a protostar, a concentration of hydrogen. Might be other gases as well, but mostly hydrogen, maybe a little bit of helium. Concentration of hydrogen, in which sustained nuclear fusion's not yet begun. And I've underlined the word sustained because there might be nuclear fusion taking place in the core of a protostar, but it's in fits and starts and it's not sustained. If a protostar accumulates enough mass, it can turn into a main sequence star. Now, we'll be talking about the life cycle of a star in lesson 98, which is the next part of this video. So I don't want to go into too much detail. But how we define a main sequence star is a ball of plasma. So it's such a high temperature, it's no longer a gas, it's now definitely a plasma. In fact, but up here where it says protostar, concentrated hot cloud of hydrogen, I think that's a hydrogen plasma as well, to be honest. So plasma, mostly hydrogen, sustained nuclear fusion in the core now. So it's very, very high temperature in the core, over 1,000,000 degrees Celsius in the core. Stable for millions of years, could be billions of years, as is the case with our star. Thousands of millions of years. And what happens here is the outward force produced by the radiation that comes from the fusion reactions is balanced by the inward force due to gravity. So that's a main sequence star. Why am I defining them here? Well, because the textbook that I'm basing this course on, there are questions in there on this chapter that need you to know what a protostar is. So fair enough. But when the solar system first formed, what we had was a cloud of gas and dust, and in the centre of that, concentrated due to gravity causing the collapse of that dust and gas, we had the formation of a protostar and the formation of bands of matter around that protostar, which over time, due to gravity, coalesced to form planets, with the part in the middle coalescing to form the star, the sun. So you can see that happening here, where you start with just dust. The dust clumps together to form small little rocky bodies, which all clump together to eventually form our planets. They will form within these bands. Sometimes they can't form into planets for whatever reason, such as where the asteroid belt is. It's nowhere near as densely packed as the pictures show. And then you've got your main sequence star in the middle. So planets, how are we going to define them? It's spheroidal, rather than just saying they're spheres or spherical, spheroidal, because they are oblate spheroids. They're slightly bulging rather than being perfect spheres, but the amount they bulge is so small you're not going to be able to see it with the naked eye. They're as spherical as they're ever going to get. Orbiting the sun, that's something that makes it a planet. If they orbit a different star, then they're exoplanets. So planets orbit the sun, and they are a planet if their orbital neighbourhood is clear of similar or more massive bodies, which is why Pluto is not a planet, because it orbits about the same distance from the sun as Neptune does, and Neptune is bigger, it's more massive than Pluto. Therefore, Neptune is the planet and Pluto cannot be. You're not going to have two planets orbiting about the same distance away from the sun as each other. One of them is the planet, that's the big one. The other one is not. And if both bodies are about the same size, as is the case with Pluto and its moon, which I think is pronounced Sharon, but it could be Charon. Someone in the comments will correct me if I'm wrong. I'm not that familiar with mythological beings, mythological characters. So I'm not sure how to pronounce that. Anyway, so Pluto and its moon are, well, they're not, they're the same order of magnitude in terms of mass. And so because they orbit each other, they're both about the same distance away from the sun. So even if Neptune wasn't there, Pluto wouldn't be able to be counted as a planet. What about Ceres? Ceres, why isn't that a planet? It's in the asteroid belt. Should be a planet, surely. It's spheroidal. It's almost spherical. It's between Mars and Jupiter. There's no other planets in that region. No, but there is an asteroid called Vesta, I think, which is very, very similar in size, just a little bit smaller than Ceres. So you can't really call Ceres a planet. I mean, Ceres used to be called a planet. Well over 100 years ago, Ceres was a planet in the solar system, and then it lost its title of planet and got called an asteroid, and it's now been promoted to dwarf planet. Everyone gets upset about Pluto being demoted to dwarf planet. Everyone forgets that it happened to poor Ceres first, and the fall from grace from Ceres from planet to asteroid is even more catastrophic. Poor old Ceres, my favourite non-planet. Anyway, that's what makes a planet: spherical and orbital neighbourhood clear. Planets could have atmospheres. They might not have atmospheres. Earth's got an atmosphere. Venus has got an atmosphere. Mars has a very, very thin atmosphere. Mercury? No, there's no atmosphere on Mercury. So whether it's got an atmosphere or not is not what makes it a planet. What about if it has moons orbiting it? Well, Earth has a moon orbiting it. Mars has two moons orbiting it. But Venus? No. Mercury? No. So it's not about whether it's got moons orbiting it that makes it a planet. There we go. So let's move on to the next categories of stuff we find in the solar system. We've got the bands here where planets were formed, but there are also other smaller bodies that formed, little rocky bodies, and we can call those asteroids. So asteroids are rocky bodies like Mercury, Venus, Earth and Mars, but they're not big enough to be spheroidal. So they're not dwarf planets, because dwarf planets are spheroidal, just like planets are spheroidal. but not big enough to be dwarf planets even. So when I say not big enough, I mean not massive enough. That's me being clumsy with my language. My apologies. So asteroids are what we call rocks that are not spheroidal enough. So I mentioned the big asteroid in the asteroid belt called Vesta. I think it's called Vesta. You can Google it. Let me know in the comments if I'm wrong. And that one is not round enough to be counted as a dwarf planet, so we call it an asteroid. There are smaller bodies than asteroids called meteoroids. Meteoroids range in size, but they are much smaller than asteroids. And there's probably some clever distinction, some clever point where a meteoroid gets large enough to be called an asteroid, but I don't know what that is. If there are enough volatile chemicals on the asteroid or in the asteroid, volatile just means things like water, which can dissolve other substances. You know, it's a sort of very strong solvent. Not that strong a solvent, but it's a solvent, that sort of thing. So there are what we call volatile, stuff that can evaporate very easily. In the asteroid, water is the best example. Then we might call it a comet. Now, there are bodies that are somewhere between comets and asteroids, and we call those centaurs. They've got a bit too much of the volatiles like water to be called an asteroid, but not enough to be called a comet. They also tend to orbit these centaurs around the same sort of distance from the Sun as Neptune. They're what we call trans-Neptunian objects. Comets come in two places in the solar system. Yeah, you do get some comets coming from around near Neptune. We call those short-period comets. One of the things that distinguishes comets from asteroids is their orbits tend to be a lot more elliptical. And a long-period comet, so those are comets where the origin is much further than the Kuiper belt. Kuiper belt is a belt around just past the orbit of Neptune. Like the asteroid belt, where it's got smaller rocky bodies in it, asteroids in it. It's like that, but it has some comets as well, and centaurs in it, and dwarf planets. And it's quite a large band of that matter, left just beyond the orbit of Neptune. It's called the Kuiper belt. If you go much further than that, you'll find the Oort cloud. And we have comets that originate from the Oort cloud. They have a much longer period. In other words, it takes them not just maybe a few hundred years to orbit the Sun, but it might take them thousands, tens of thousands of years to orbit the Sun. Usually we don't really care much about those comets that are found in the Oort cloud until some interaction between them, some collision, some gravitational interaction, causes a comet to change its trajectory just enough that it falls close enough to the Sun, and then we'll get an announcement to get your telescopes out and have a look, because there's a really big comet that we have never seen before, and we all get very excited about that sort of thing. So that's comets, asteroids. The Goldilocks zone, I mentioned that Earth is within the habitable zone. Another name for that is the Goldilocks zone, because it's a place where it's not too hot, not too cold, just like Goldilocks's fabled porridge adventure. Anyway, so you need to have a distance from the Sun where the liquid water can exist on the surface of the planet. Mars does have liquid water on the surface at certain places, but mainly it's because that liquid water is so very salinated. Is that what you call it? It's very, very salty. So the pressure, the atmospheric pressure on Mars is very low, so the boiling point is very low. But if you have very salty water, then you can get flowing liquid water on that surface. And there's not a lot of it, but there's enough of it that it falls within the category of being in the habitable zone. Venus, way too high a temperature to be in the habitable zone, and Ceres or Jupiter, way too far out to be in a habitable zone. But in order for there to be liquid water on the surface, as I've said, you also have to have a dense enough atmosphere. Mars, just about, but only with the saltiest of salty waters. So that is almost everything we need to say about that. I suppose we need to talk about this bit down here, the definition of an ellipse. I said comets have an eccentric elliptical orbit. Well, so what's an ellipse? Well, it's kind of an oval. you might start by saying an ellipse is like a squashed circle, but that's not good enough, really. This is how we define an ellipse. If you imagine we are drawing, we've got 2 points, just 2 arbitrary points placed down here, and we draw a line from one of those points to a surface, or to an edge as it is here, a line, and then back to the other point. The length of those 2 lines, the red line and the blue line, when added together is always the same. So the shape that is cast out by that line, those 2 lines as they are put at any angle you like so that they're the same length, that shape is an oval. Yes, it is an oval, but that's too vague. It's an ellipse. So orbits are elliptical. All orbits are elliptical. And if these 2 points, we call those foci, plural of focus, if these 2 foci are at the same point, then your red line goes out to the edge, the blue line comes straight back again, so the red line is the length of the radius, the blue line is the length of the radius, the red line and the blue line added together is the diameter, and we have a circle. So a circle is a type of ellipse, and planets tend to have almost circular orbits. Asteroids have reasonably circular orbits, usually, but comets have usually much more eccentric orbits. So all orbits are elliptical, and a circle is a type of ellipse, where the sun, or whatever body is being orbited, if it's a moon we're talking about, the planet that is being orbited by the moon, that is at one of these foci. What happened there? That's at one of these foci. The other one, there's just nothing there. There's no significance. But you place a planet at one of these foci, a moon can orbit with an ellipse around it. Or if you place the sun at one of these foci, a star, a planet. Why am I tripping over my words? Place the sun at one of these foci, and a planet will orbit around it in an ellipse. So that's what we mean by elliptical. More eccentric means the 2 foci are further apart. So you get a more squashed ellipse. And up here, what force is it that pulls the stars and the sun? The stars. What force is it that pulls the gas into a protostar, pulls the protostar into a main sequence star? All the accretion region around the stars pulls those into planets. What force is it? It's gravity. Gravity is what is doing all of that. There are some fun videos out there on the YouTube that talks about how gravity doesn't exist. That's all good fun. It's not just me. The scientific community places that in the same category as silly thought experiments about what if the world was flat, silly thought experiments like that. They're fun to think about for a bit, but there's no basis in reality. It doesn't take a lot to disprove those sorts of theories. I say theories in a very loose sense. They're not theories because theories have to have something to back them up, and they certainly don't. So let us move on then to Lesson 98. Lesson 98 is about stars and how they evolve over time. I love this image. Again, I stole this from Wikipedia, Creative Commons license. It's all above board. Starting at the top here, the life cycle of our sun. Our sun is about here in its life cycle. So this is in billions of years. 1, 2, 3, 4, 4.5 billion years. That's how old our sun is, from when it first became a star after it was a protostar. And then we've got 6, 7, 8, gradually warming up over that time. If you're going to say, that's why there's global warming, look at the time scale. It's billions of years. Global warming is not caused by the sun's natural phenomena where it's going to increase in temperature over the next few billion years, because the spike in global temperatures has happened over the last 50-odd years, even less than that. No, it's our fault, not the sun. Stop trying to blame other people for humanity's failures. Anyway, get about 10 billion years and we start to see problems. The sun is going to expand into a red giant. Mercury, Venus, probably Earth will become bodies within that star, so they'll be vaporized, ionized indeed, completely gone. The red giant will then collapse. Well, the core of the red giant will collapse. The outer layers will continue to expand outwards and form a planetary nebula. Within its core, very dense, dead star called a white dwarf, which over the next many hundreds of billions of years will cool into a black dwarf. And that's the end of that. So, our star is the third, we think, the third star that's recycled the same matter in this particular little part of the galaxy. That's what we think. The first star would have been entirely hydrogen, tiniest bit of helium perhaps, but almost entirely hydrogen. So that hydrogen gas would have been found in what we call a nebula. That's a cloud of gas. It could be a cloud of dust and gas, but for the first time round this loop, there's no dust, there's just gas. Then gravity causes the slightly denser parts of that cloud to collapse in. The same way as when I drop something, gravity pulls it down. Gravity pulls mass together. So gravity is going to pull those denser parts of that cloud of hydrogen gas together. And when the hydrogen gas, in these little clouds, when the hydrogen gas packet, or I don't know what you call it, the little dense part of the cloud is compressing down. What we're doing, of course, as you're falling, as matter falls due to gravity, energy is transferred from the gravitational potential energy store to the kinetic energy store. But what is the kinetic energy store? What would we use to describe that when we're talking about atoms of hydrogen? They're very, very, very small. So what we're talking about there is the individual atoms of hydrogen moving faster. So we would experience that as an increase in temperature, right? You get the atoms moving faster and jiggling faster, that's a higher temperature. So the gravitational collapse of this cloud causes energy to be transferred from the gravitational potential energy store to the kinetic energy store of the hydrogen atoms, molecules, which is therefore being transferring that energy into the thermal energy store of the gas cloud. So the gas cloud's thermal energy store increases, the temperature increases as it collapses. And if the temperature gets high enough, we're talking about tens of thousands of, maybe even hundreds of thousands of degrees Celsius, then you can start to get fusion reactions occurring. So what happens there? We've already talked about nuclear fusion in video 7. The hydrogen nuclei, they're going to be nuclei now because at that temperature the electrons can't stay married to the atoms. The electrons are moving around the nuclei, but the temperature's so high, the atoms are colliding with each other so fast that the electrons just get knocked off all the time. So we've got a plasma now. So it's glowing. So these very dense packets of gas are glowing. They're emitting light, but they're not yet stars. And then we're going to have protostars forming, where you get fusion sputtering in the middle of the core of these gas clouds, these very dense gas clouds. Of course, as soon as fusion starts, it produces radiation. That radiation is going to push outwards, which is going to reduce the density of the cloud slightly, reducing the pressure in the middle, reducing the temperature, and the fusion stops. And it collapses again. Temperature increases, fusion starts, pushes it out, fusion stops. So you've got that going on in a protostar, little flashes of fusion, but not really sustained fusion. But the rest of the cloud is still being attracted down towards that protostar. So the mass of this protostar continues to increase. And so the temperature in the core, yes, it's sort of sputtering a little bit, but it does continue in general to increase, until you've got sufficient mass that you can have sustained nuclear fusion. And then you end up with a main sequence star. Now, I'm going to go around this on the right loop. Let us suppose that our protostar accumulated enough mass to be a very high mass star. Now, if we went round this route, you would then have a stable star where the fusion reaction is causing radiation pushing outwards. Sometimes that's called radiation pressure, but I really don't like that term because pressure is force divided by area, and you can't balance a pressure with gravitational force. You have to balance forces with forces. You can't balance pressure with forces. That doesn't make sense in physics. But astronomers say it all the time. Because, you know, when you become an expert in your field, you can be a bit more relaxed with the way you describe things. It's only exams at school that are really, really fussy. Anyway, the high mass star, the core of it is a very, very high mass. The core of it is going to have fusion going on. So there's radiation pushing outwards, gravity's pulling inwards, and those two forces balance. So the star stays about the same size. Now, the massive star we're talking about the first time round, which contains at the start almost entirely hydrogen, or a little bit of helium, but almost entirely hydrogen, that sort of star is going to, because of how massive it is, because of how high the temperature is, it's going to be blue. Remember what we talked about in the previous part? We were talking about thermal energy, I think. We might have done it when we talked about waves as well. I can't remember which video, but we've done it at least twice. Here's the three receptors within our eyes, the three cone sizes, small, medium, and large, and how we perceive colour. This curve shows a normalized curve to show the wavelengths emitted by a body at different temperatures, and these are the temperatures of the body. So we get up to about 3,000, 4,000, 5,000 Kelvin. It looks white. And if we carry on increasing the temperature, we now get more blue than red, so the star starts looking blue. That is things like Spica, very, very, very bright star that you can see quite close to the horizon in the UK. Spica, very bright blue star. It's not going to last very long, relatively speaking. We could be looking at hundreds of thousands, maybe millions of years. Certainly not billions of years. It's too high a mass. Fusion's happening at too quick a rate. We're using up that hydrogen too quickly. Now, what will happen is, when in the core we're running out of hydrogen, those fusion reactions will reduce the rate. The rate of fusion reactions will reduce. So the amount of outward force caused by the radiation, which is produced by those fusion reactions, that decreases. But all that mass is still there, so which means that the mass of the star is still going to cause the star to collapse further. So the core of the star is going to collapse down a bit further. Now, when it does that, it means the temperature of the core goes up. This is the tricky bit. And so, because the core temperature and pressure goes up, it's now able to fuse heavier elements. It can now fuse the helium and the hydrogen to make maybe lithium. And then it can fuse higher and higher and higher up the periodic table as it collapses further and further. But as it does that, it produces more radiation pushing outwards on the outer layers, so the outer layers get pushed out further and cool down, while the core collapses down further and heats up. So the outer layers end up being cool, and as we know, red is what is emitted by pretty hot bodies and thousands of degrees Celsius. What was it, 3,000, 4,000, 3,000 degrees Celsius, it's going to look red, but it's not going to be, it's going to be really, really, really high temperature right in the core. So it's just the outer layer is very cold, relatively speaking, not as dense, relatively speaking. So Betelgeuse, that is how you pronounce that, is an example. You can see Betelgeuse in the Orion Nebula. Orion Nebula? The Orion constellation. My apologies. You can see it is red. It's got a reddy sort of look to it. You can see it. That is a red supergiant. Now, eventually, we're going to be fusing elements up towards iron on the periodic table. And you can't fuse in the core of a star, you cannot fuse elements heavier than iron. Because as you fuse elements that are lighter than iron, by lighter I mean less mass than iron, to form something which is getting closer and closer to iron on the periodic table, we're going that way up the periodic table in terms of mass, that causes more energy to be released from the fusion reaction than needed to go in to make the reaction happen. If you want to fuse elements that are more massive than iron, then actually you have to put more energy into the reaction than you get out. So that would have an overall cooling effect, and that doesn't happen naturally. In order to get that to happen, to fuse those heavier elements, you would have to have much more energy going into the reaction. So how do you get that to happen? Well, that's where gravity comes in again. When the core starts to cool down much, much more, because we're now fusing close to iron, so there's the fusion reactions drop very, very suddenly, very rapidly. The outer layers, which are still being pulled together by gravity, are going to be attracted in, and it's going to be like a gravitational particle accelerator. They, on opposite sides of this red supergiant, are going to be pulled towards each other and accelerate and get faster and faster and faster. There's your extra energy. When all that matter comes smashing in into the middle, the temperature rockets up, and we are now able to fuse elements heavier than iron. Now, this is a little bit of a fiction here, because a lot of the periodic table elements, even a supernova of that kind, doesn't have enough energy to form them. You need to have supernovae caused by the collision of neutron stars, for example, to fuse really heavy elements. But we're not going to go into that sort of level. This is okay for now, and if you're interested in things like supernovae, which is the plural of supernova, yeah, look it up. It's a fascinating subject. Where do all our elements come from? What I'll tell you at GCSE level is evidence for this process is the fact that elements heavier than iron, by which I mean more massive than iron, exist on Earth. If elements more massive than iron exist on Earth, then the Earth is made out of the remnants of supernovae. So this must have happened, because otherwise there's not enough energy in any interaction to make those elements that we take for granted. There's gold on Earth. Where did the gold come from? It cannot form in the core of a star. So where did it come from? It had to form in much higher energy interactions like these. Not quite this, but like these. So you end up with a supernova, and then depending on what's left, if you have a core of that supernova, the bit in the middle, which is sufficiently high in mass, sufficiently dense, it can tear space-time itself. That's the way I'm going to describe it to you. A black hole is an incredibly dense body in the universe, in an incredibly dense body, so dense that there is no path light can take to go from inside the black hole to outside. It is possible for matter to fall in, and that's interesting, and there's a lot of really interesting physics about why that is the case, why there is a way of getting matter into a black hole but not out. By all means, look this stuff up, because it is really interesting, cutting-edge physics stuff. We're not going to go into it now. We'll often at A-level talk about the escape velocity, that is the speed that something would have to move to get away from the body. We talk about the escape velocity being greater than the speed of light, and that's why light can't escape a black hole. Well, that is true, but that's not the whole story. Black holes are much more exotic than that. Black holes are an area where our understanding of physics truly breaks down, and we are, even now at the frontier of physics, trying to get a hold, kind of get a handle of the physics of black holes. In physics, we've got, I'll just take a slight aside here because I think it's interesting. In physics, we've got two different frameworks for physics. We've got a modern physics that describes how very, very small things behave. We call that quantum physics. And we've got a modern physics that describes how space and time behaves on the very big scale. We call that general relativity. And those two, how physics of very big things and the physics of very small things, they have contradictions within them. Real fundamental contradictions in how those two physicses work. They're two very different frameworks of physics. Well, black holes are incredibly massive, so they warp space-time around them in a way that's consistent with general relativity. But they're also singularities. They're so dense that they collapse into what we would call a singularity, and that's small. So the physics of very small things is quantum physics, and so we're now going to have to describe this object called a black hole, where it's very small, so we're looking at what happens with quantum physics, but it's very massive, so we're looking at with general relativity, and those two theories contradict on a fundamental level to do with the nature of space and time. They really contradict. So what do? Well, we do what physicists always do. We make better models. That's what we're currently, as of 2024, we're still working on it. We make better models. That's what we do. Right, so if it's not massive enough to form a black hole, you'll form a neutron star. Neutron stars are not, well, I mean, they are the second prize, the silver medal winners of the universe, but don't underestimate how absolutely bonkers they are. Basically, the matter is so dense that atoms get squished together so that the electrons and the protons in the atoms combine to form neutrons. This is a gross simplification, but this is what we're going with. Electron capture. So atoms' nuclei, the atoms that make up the body, the star, their nuclei stop having protons in them because the protons and the electrons in the atoms combine to form neutrons. So when you've got an atom nucleus that has only got neutrons in it, there's no positive charge repelling the nearby nucleus. So those nuclei of atoms of atomic number 0, because they contain no protons and have no electrons anymore, there's nothing stopping them from getting really, really close together. So effectively, you form a single nucleus with a diameter about the size of a city. The nucleus, there's no gaps. It is effectively a nucleus that contains only neutrons and is about the size of a city. The density of this thing is, well, if I said astronomical, that would be an unnecessary pun. Of course, around the outside of the neutron star, where it's a bit less dense, you'll still have protons, you'll still have fusion going on, so there's still going to be lots of light coming off of this thing. It's still a star, but you don't have fusion in the core anymore. You have fusion outside the core, and the core is just a whopping great big atomic number 0 nucleus. It's huge. Absolutely bonkers thing. They spin ridiculously fast, spitting X-rays in all directions. Well, not in all directions. Well, yeah, sort of. They spit a beam of X-rays, a beam of gamma radiation that they then spin round, and they, like a flashlight, casting that out into space. Incredibly fast when they do it. Huge things. Anyway, neutron stars are exciting. So you can get neutron stars. You can also, or you will also, have other matter which just forms a nebula. It's just the remains of it that gets pushed out from the supernova. When the new supernova is an explosion, so it pushes matter out. You've got the bit in the middle, black hole, neutron star. But you'll also have the nebula. And that nebula now contains elements heavier than helium as well. Now we go around again. So let's now go the left way. So that nebula, gravity pulls it in, forms a protostar, pulls it in, fusion starts in the core, we then get a main sequence star, just as we had last time. This time it's much less mass, so it lasts much longer. We might get something like our sun that's going to last for around 10 billion years. Same thing happens. The core collapses a bit further because the fusion reactions of hydrogen reduce, the rate of those reactions reduce because we're using up hydrogen, so we're going to have to fuse the heavier elements, so everything collapses down. The outer layers puff out, just like we had last time. The outer layers puff out, but this time the outer layers continue to puff out. There's not enough mass to form strong enough gravity to hold those outer layers around the star. With a supergiant, those outer layers are never going to escape forever. They collapse back in to form the supernova. But with a red giant, the outer layers just carry on puffing out. And although they're attracted back to the star, they're not attracted enough to cause that collapse. So those outer layers continue to puff out, and they kind of form a bubble around the bit in the middle. We can see that. When that was first observed, it had some physical size to it in the same way as planets do when you look at planets through a telescope. But unlike planets, they also didn't have definite edges. They were kind of blurry, a bit nebulous, a bit cloud-like, but also kind of round and had some physical size in the sky, as it looked like, angular size. So they weren't called just nebulae because they weren't all sort of irregular. They were called planetary nebula because they kind of looked a bit like planets. It's got nothing to do with forming planets in this region. It's just because of how it looked to early astronomers. Now, the bit in the middle will be a white dwarf. It will continue collapsing down, and it will get colder and colder and colder, and eventually, after hundreds of billions of years, it will form a black, maybe even thousands of billions of years, it will form a black dwarf. Incredibly dense, really is very, very, very dense, but it's just matter that's incredibly dense, and so it's nice and hot. When something's hot, it glows. It can glow white hot, but it will cool eventually, because if it's glowing, it's emitting radiation, so that means there's waves transferring energy out of that body, out of the thermal energy store of that body, so eventually the body will cool down and will become a black dwarf. It takes a long time. The universe isn't old enough to have formed black dwarfs yet. Not according to any of our theories, and that's why we haven't seen them yet, because the universe isn't old enough. What about the nebula? Well, the nebula that puffs out, here we go again. We're going to go around, and so we can go around a third time. We believe that the sun that we orbit is a third time around these loops. Now, I don't know whether it went the right-hand loop twice and then the left-hand loop once, or what, I don't know. If there's not enough mass that collects together from the nebula, then we're not going to form a big main sequence star. We might form something like a red dwarf. Red dwarfs are hot enough for nuclear fusion to happen in the core, so they are stars, but they're so small that they are not that hot. They're quite cool. But as the inner layers, you don't really have inner layers and outer layers, they're too small for that. So as it collapses down and fuses to get those heavier elements, it will get hotter and hotter, which is why it forms the blue dwarf and eventually collapses into a white dwarf. But there's not enough matter to puff out. It's not big enough for that, so you just have that little lump that follows that path. So that is the... sometimes it's called the life cycle of stars. I don't like that terminology because it's not really a cycle. You can go around it a few times, but eventually we're going to run out of gas to make stars with. And that's effectively what we're doing here, is we're taking gas in a nebula and we're stopping it from being gas. We're turning it into other things until eventually we don't have any gas left. And then we've got the future, which is a universe of black dwarfs, black holes, and neutron stars. Neutron stars will merge and form black holes. So the future is just black holes and black dwarfs. And they get so spaced out, because the universe is expanding, we'll talk about that later, that there's nothing can happen. Right, so let's go down here and check it. I've covered everything. Stars age, and they use up hydrogen. Yep, said that. Fusing heavier elements make stars less stable. That is true. And eventually when they're fused, heavier, not heavy, heavier, still lighter than iron. And eventually they're going to puff out their outer layers completely, or supernova. A fusion explosion caused by the collapse of a red supergiant. It says creates heavy elements such as uranium. That's a bit of a stretch. There are different types of supernovae. The one that's described in this picture, I don't think would fuse uranium. I think to get uranium from fusion, you'd have to have neutron stars colliding. But look it up, see if I'm wrong. Let me know if I'm wrong. Star's colour depends on its temperature. We've covered that already. Right, let's move on to lesson 99 then. Lesson 99. We're back down to planets again. Planets, satellites, and orbits. So orbits are elliptical, as I've already said. I think it was Newton, might be Galileo, but I think it was Newton. Someone will tell me if it was Galileo and I'm wrong. I think it was Newton who proposed this thought experiment. Imagine we had a cannon on top of a mountain, was shot a cannonball. What path would that cannonball take? Well, if the Earth was flat, the cannonball would follow a parabola. It would have a parabolic path. And very often in physics, that's what we say. Because on the small scale, you know, the Earth looks pretty flat to me, but that's because I'm small and the Earth is big. So that's why the Earth looks pretty flat near me. So we'll think it's a parabola. Actually, it's not a parabola. The orbit is actually an ellipse. And Newton knew this. He figured this out. And he said, well, look, if I shot the cannonball faster what would happen to the path? Well, it's an ellipse, so it'd end up hitting the ground further away. But as the cannonball is falling, the Earth is curving downwards away from us. So, if I do it sideways, the ball is falling, cannonball is falling, and the Earth is curving away from it. So, if we shot the cannonball fast enough from the top of this mountain, it would fall towards the Earth at the same rate that the Earth's curvature falls away, so that we would end up going on path C, a circle. And Newton said, look, what if I shot it faster? Well, if I shot it faster, I might go in an even bigger circle like this. If I shot it even faster, I might even get it to escape the Earth altogether. Proposing space travel in the 1600s. So the idea of orbits relies on the idea of a spherical Earth and matter being attracted to the centre of this spherical Earth. Circular orbits. Orbits are all elliptical, but a circle is a particular type of ellipse. I've got these animations here to show the same idea. That there's the cannon on the top, there's the green ball hitting the surface. Now, if you look at this picture on the very bottom, I wonder if I can zoom in and it still animates. Yes, good. If you look at this picture, have a look at the arrows. We've got this flashing pink arrow, which is the velocity of the green cannonball. We've got this red and yellow flashing arrow. That's the direction of the gravitational force towards the centre of the Earth. And the velocity and the force are perpendicular to each other. Now we know, pen out, we know that work done is equal to, let's write it, where should we write it? Let's write it here in small. Well, work done is equal to that force multiplied by displacement. And therefore power, which is work done divided by time, is equal to the right-hand side divided by time. So power, that is the rate that we put energy into an energy store, the rate that we transfer energy, is force multiplied by velocity. V is S over T. So we've got power, the rate that we transfer energy. That's a dot. So if you remember when we overemphasized the importance of the difference between a dot product and a cross product, a scalar product and a vector product, this is a scalar product, and so F and V have to be in the same direction for there to be work done. And if F and V are perpendicular, no work is done. So the power, the rate of doing work on this green cannonball is 0. No joules per second are transferred into the kinetic energy store of this cannonball, even though there's a gravitational force acting the whole time, and even though it's moving with a velocity, because F and V are perpendicular, so no work is done. This is the sort of thing that is the reason why when I teach this to my classes, even in GCSE level, I teach cross and dot products. Not a lot of people do that because it's quite advanced stuff. So effectively, the ball is always falling because it's experiencing gravity and being accelerated by gravity in the direction of the red and yellow flashing arrow towards the centre of the Earth. But because the velocity is perpendicular to that acceleration and always is, we're moving fast enough to make this happen. If we went any faster, it would be a larger ellipse. Went any slower, it would be a smaller ellipse and we'd hit the Earth. But if we get the speed just right, then we are going to be going in a circle with circular motion. So that's what happens. That's what orbits are. So it says here that the force is towards the centre. We call that a centripetal force, a centre-seeking force, a force that always points towards the centre of a circle in circular motion. We can do some maths on this. We could say, well, because we're moving in a circle, the circumference of a circle is going to be 2 times pi times the radius. We can say that the speed we have to move is the displacement divided by the time. And we can say, well, the displacement in one rotation is one circumference. So we call a rotation a time period. We did that in waves. So we can say that the displacement is 2 pi r and the time period is t. So the speed of the orbiting satellite, in this case, could be the moon we're looking at, is 2 pi r over t. And if you know the distance to the moon, and you know the moon takes 1 month to go around the Earth, roughly, then you can use 2 pi times the distance to the moon, divided by the time it takes for the moon to go around the Earth, equals the speed of the moon. Or you could do it for the Earth. We know that the Earth is roughly 150 million kilometres, I think that's right, 150 million kilometres from the sun. Someone will correct me if I'm wrong. We know that the time period for the Earth around the sun is 1 year, so 365 days. If you want to know the speed of the Earth in meters per second, you just got to chuck those numbers into that equation. You can get the speed of the Earth around the sun. It's just speed equals distance over time, but the distance is a circumferential distance. It's the circumference. So circular orbit, speed doesn't change, but the velocity does. Why is that? Because velocity is a vector and the direction is changing. Therefore, there is acceleration because the velocity is changing. And the acceleration, F equals ma, the acceleration, A, is directly proportional to F, the force. So if the gravitational force is in a particular direction, then the acceleration is in the same direction. So it says here, acceleration is the rate of change of velocity, so the body accelerates, even though the speed remains unchanged. The acceleration is the same direction as the force. Newton's second law, F equals ma. So I've covered that box there. Let's look at this one up here. Body moves too fast, it leaves its orbit. That's path D and path E. Body moves too slow, it falls. That's path A and path B. Certain distance, a certain speed will have circular motion. Super. So why do we care about that? Well, because what we like doing nowadays is putting bits of metal in space, satellites, putting them in space. And there are two different types of orbit. Well, there are lots of different types of orbit. There are two interesting types of orbit for satellites in space. There is the geostationary satellite. So here is an animation showing a geostationary satellite. What you're looking at there is the northern hemisphere. There is the North Pole right in the centre. And we are looking at some point on the Earth's surface. Let's say it's this point down here at the bottom of this yellow line. If you have a satellite travelling at just the right speed, at just the right distance from the Earth, then it will always be directly over the same point on the Earth's surface. That's really useful, because if you are at the red place here on the Earth's surface, and you wanted to send a signal to someone over on the other side of the Earth, you've got two choices. Run lots of cables, it's going to be expensive, or bounce a radio wave off a satellite, and then the reflection of that can be detected on the other side of the Earth. So you want to get a signal from one side of the Earth to the other. It's difficult because the Earth's in the way. You can run lots of cables, or better, you can bounce a signal off a satellite. But if the satellite is going to be in a different place in the sky at different times of day, different times of the year, then you're going to have to point your satellite dish at the satellite and be adjusting it to keep bouncing that signal off. And so's the receiver going to have to be adjusting their position. Well, satellite television used to be very popular in the early 2000s. Late 90s, and as I look now, I'm looking at some houses and they all have satellite dishes on the roofs, so I guess satellite television is still popular to some people. Those dishes don't track satellites, they just sit there pointing at the same patch in the sky, and they sit there pointing at a patch in the sky where there is a satellite in a geostationary orbit, the right distance from the Earth, and travelling the right speed so that it is always appearing in the same place in the sky relative to the Earth's surface. So I don't have to move my satellite. Fantastic. There's a few things then. You have to have the satellite the right distance, yes, the right speed, yes, but also it has to be over the equator. So satellite dishes for satellite television will always point to the south and possibly some angle as well, but they'll always be pointing generally to the south, because in the northern hemisphere, if you're in the southern hemisphere, they're always going to point north. That's how geography works. I don't know. I'm not a geographer. So that is a geostationary satellite, really useful for communication, so telecommunications and television, that sort of thing. The other type of satellite is a polar satellite, the other type of orbit. This is one where the orbit takes you over the poles. So I've just traced the whole orbit here, and if you look, at some point in the day, the path of the satellite is over every point on the Earth's surface. So if you have that satellite going round and round and round and round and round and round and round, and it can go reasonably quickly, it doesn't matter, you know, the ISS, the International Space Station, it takes less than 2 hours to go around, more than 1 hour, less than 2 hours to go around the Earth entirely. Every time it goes round it, it's going to see a different part of the Earth's surface. Look, now it's just gone over Australia, now it's gone over India, now it's gone over South Africa, now it's gone over Brazil, now it's gone over California, middle of nowhere, and then we're back around to Australia, India again, and every time it goes round, it goes over a different part of the Earth's surface. So what might those satellites be used for? Well, weather satellites. If you want to track how clouds are moving so you can make weather predictions, that's a really useful type of satellite. You can use this not just for weather monitoring, but any sort of monitoring. So if you were in the military and you wanted to investigate the movement of some hostile military forces, then you could have a satellite taking pictures every time it goes over the particular place where you think there might be some enemy encampment, and you can get updates on those pictures and see what's going on. And because it's in space, it's really hard to stop it from being able to see what you're doing on the ground. To my knowledge, there has been no space warfare yet. Got a little bit dicey in the 70s and 80s, but as far as I know, there has been no space warfare yet. So as far as I know, no satellite has been shot out of the sky to prevent it from spying on places on the ground. But then you've got places like North Korea did nuclear weapons testing underground, so the satellites couldn't see. We know that happened because of seismic activity and because of isotopes that were detected in the atmosphere after that corresponded with to that seismic activity. So we know that nuclear weapons testing has happened in North Korea. The evidence is all pointing to it. Spy satellites, useful for looking for other things as well. I mean, not traffic, you'd use airplanes for that. No good for communication, though, because the satellite's always in a different place in the sky. So there we go. I've got a map up here which shows different orbits of different satellites around the Earth. And this is to scale. I like the axes on this. If you go from the centre of the Earth outwards, we've got the radius of orbit from the centre of the Earth. So this is 10,000 kilometres, 20,000, 30,000, 40,000 kilometres. Or if you're absolutely insane, we have it in miles as well. No one in their right mind would use miles in this day and age, but there they are. We've also got the height above sea level. So, you know, the radius of the Earth is about 6,400 kilometres. So you subtract that from each of these numbers, and you get 10,000, 20,000, 30,000, and so on. And again, this archaic unit of miles. We've also got other axes for time. So we've got this one here, the orbital period. Here it takes 5 hours to go around the Earth, 10 hours, 15 hours, 20 hours. If you want a stable circular orbit of this satellite that takes exactly 20 hours to go around the Earth, you stick it there, that distance away from the Earth, about 30,000 kilometres above the sea. And on the other side, we've got how fast the satellite has to move at that distance to get a nice stable orbit. So we've got 20,000 kilometres per hour, 15,000 kilometres per hour, 11,000 kilometres per hour. You'll notice it's getting slower and slower the further out you go. You'll also notice it's not a linear scale. It's interesting. Over here, in fact, the time period isn't a linear scale either. Over here, we've got something called 𝗟𝗶H, or it might be 𝗟𝗶, which I think is miles per hour, which is another archaic unit that needs to die, but there we go. And then we've got a bunch of satellites. So GPS satellites, our GPS satellites that orbit the Earth, and we use those GPS satellites in order to triangulate our position on Earth. That's where they sit. And there are other positioning satellites, like the GLONASS satellites. They're all in the same sort of part of space. Go a bit further out, the geostationary orbits, this is where your sky television satellites are, they're much further out. The International Space Station, those beautiful pictures you see where you can see the curvature of the Earth's surface, those pictures taken from there, right next to the Earth. That is space. People that take a visit to the ISS and are visiting space, it is like camping in your back garden and saying that you are experiencing the wilderness. It's, we are protected from most of the radiation from the sun by Van Allen belts. Now, if you're interested in all this stuff, listen, I've got a whole series of GCSE astronomy videos, 16 GCSE astronomy videos, which go in much more detail into all this space topic. I've already been talking for an hour, and we've still got 2 lessons left, so I don't want to talk much more than this. Hubble Space Telescope is there and all this sort of thing. But anyway, there we go. That is, I think, an interesting picture for you to ponder and understand the scales of things. And when you see pictures of the ISS and it looks like it's skimming the atmosphere, it kind of is. Look how close it is. Right, let's move on to lesson 100. And wouldn't it be lovely if lesson 100 were the last lesson, so there's a nice round number of lessons? But no, there are 101 lessons. Lesson 100, the expanding universe. So we know that the universe is expanding. This is not up for debate. We know the universe is expanding for a number of reasons. Stars emit a broad spectrum of light. You look at the light from the sun, it's white light from the sun. But if you take that colour spectrum from the sun and you analyse it really carefully, you find that there are colours missing. You don't usually see this. It's very interesting, but there are colours missing. Very, very thin black lines on our continuous spectrum. Now, why is that? Well, that is because of what the sun is made of. If you take hydrogen on Earth, a gas of hydrogen, and you excite it, it will glow. But it will glow only at certain wavelengths. It will emit this red here. It will emit some green down here, a bit of blue down here, a bit of purple. It will emit certain colours. So if you take hydrogen and make a star out of it, then those elements are, rather than emitting that light, there will be some of that going on, but it's too energetic for electrons to de-excite and emit that light. But you are going to have the preferential absorption of those colours corresponding to the same colours. So we see this absorption spectrum showing dark lines where colours have been absorbed by matter in the atmospheres of the stars. Now, an interesting one is this yellow one here. When we started doing spectrometry of stars, we found that there was a yellow dark line that we could not find any elements on Earth it corresponded to. The sun contained an element, and we didn't know what that element was. So we named it after the sun. I think it's Greek. Someone will correct me if I'm wrong. The word for the sun is helios, so we called it helium. We discovered it on the sun, but we'd never found it on Earth. And then we did. So helium was first found in the sun. I find that fun. Anyway, we've got the elements that make up the sun there. Now, most stars, in fact all stars, contain hydrogen, amongst other things. And hydrogen has a characteristic spacing, relative spacing of dark lines. A characteristic spacing. So any star we find, if we analyse the spectrum emitted from that star, we will get the same characteristic spacing. And if we look at nearby stars, that's exactly what we see. galaxies are made out of stars. So if we look at galaxies, we'd expect to see the same thing. And if we look at things like the Magellanic Clouds, which are satellite galaxies orbiting the Milky Way, we see the same spectrum. What's really interesting is when we look at galaxies that are farther away from us. Now, I'm not going to talk about Andromeda at the moment because that's a special case. That's a galaxy which is actually our nearest galaxy within our cluster, and that's breaking the rules slightly, and I'll explain that in a second. But if we, and this is what Edwin Hubble did, if we look at galaxies farther and farther and farther away, and we look at the spectra from them, we find that the farther away they are, the more these black lines seem to have bigger wavelengths than they should. Now, we call this redshift, the increase in the observed wavelengths of the dark lines on the absorption spectrum compared to the wavelengths of the light that we would get for a body that is not moving, that's not far away from us. And what this shows, this redshift indicates that the galaxies are receding away from us. That's the physics. That's what it says. The only way to get this redshift is to have galaxies that makes physical sense, is for galaxies to be moving away from us. There were various other theories that were proposed, like the tired light theory. The wavelengths must just get bigger over time as light travels through space. But there's no other evidence. If you adopt that as a theory and then test it against other observations, it breaks down. Whereas galaxies moving away from us, well, that matches our observations, so that is what's happening. And it turns out that if you map a graph of the galaxies versus their distance from us, the distance of the galaxy from us, and the red shift, which you're more red shifted, the wavelengths are increased more if we're moving farther. That's just, it's using the same physics as Doppler shift. An ambulance goes past us and you hear the pitch of the ambulance siren dropping when it's moving away from us. So using the same physics to calculate the redshift as a speed of recession away from us, a recessional velocity, a speed that something is moving away from us, what do we get? We get a straight line. That's interesting. Passing through the origin. That's very interesting. Now, there are points that don't lie on this line. Andromeda happens to be close enough to us that it's actually moving towards us. The gravitational attraction between the Milky Way and Andromeda is so strong that the two galaxies are actually moving towards each other. But you don't see that. The farther out you go, you just start seeing galaxies moving faster and faster and faster away from us. Now, this is interesting. On the x-axis is distance. It's an odd unit, megaparsecs, and if you want to know what a parsec is, look at my astronomy videos. But it's a big unit of distance. And we've got redshift. That's a speed. Okay. So the gradient of this graph would be a speed divided by a distance. A speed divided by a distance. Well, what is a speed? So let's just write some things down here. Pen. So the gradient is a speed divided by a distance. And what is a speed? A speed is a distance divided by a time. And that's all divided by a distance. Okay, so distance is there. Speed is distance divided by time. Distances cancel. We're left with the gradient being 1 over a time. But what is that time? Well, that time is the time that a body travelling that speed travels that distance. That's what that time is. How long it takes for a galaxy moving yay fast to go yay far. And this is a recessional velocity. I keep saying speed. It is a vector. It is velocity. It's a velocity away from us. So the gradient is 1 divided by the time that a galaxy has been moving away from us, if it's travelling at the speed it's travelling, and it's the distance away from us it is. And because it's a constant gradient, then 1 over time is constant. So the time must be constant. So the amount of time that every galaxy, apart from Andromeda, amount of time that galaxies are moving away from us is the same. Works out to be just over 13 billion years. Not just over, 13.7 billion years. So that means that galaxies, all of the galaxies, apart from Andromeda, all of the galaxies have been moving away from us for 13.7 billion years. Which means that 13.7 billion years ago, all the galaxies were here. All of them. The whole universe on top of itself. It was all in one place. This is a huge piece of evidence for the Big Bang theory. If all of the matter in the universe was originally here 13.7 billion years ago and has been spreading out, then that shows not that things are moving away from each other. If that was the case, there's no reason why something farther would be moving faster. No, the only reason something farther is moving faster is because the space between the galaxies is expanding. Have a look at this animation and you'll see what I mean. The points that are close together don't seem to move away from each other. Look at these 2 points. They are not moving away from each other quite as fast as the points that start far apart. So these two, oh, you can't see it. It's moving too fast. But the points that are far apart moving faster, the points that are close together moving slower, means that the amount of space between the points must all be expanding. So there's more space between the points and the space all expands uniformly. Then because there's more space, space expands faster between those points. Let me try and explain it another way. Imagine I have a ruler, a normal ruler, but this is a magic ruler. And every year, each centimetre gains 1 millimetre. Every year. Well, the 1 centimetre and the 2 centimetre mark are 1 centimetre apart. But a year later, they're a centimetre plus a millimetre apart. The 1 centimetre and the 2 centimetre mark start 2 centimetres apart. After 1 year, they're now 2 centimetres and 2 millimetres apart, because each centimetre has gained a millimetre. The 1 centimetre and the 10 centimetre mark start 10 centimetres apart. Actually, they start 9 centimetres apart, don't they? 0 and 10 are 10 centimetres apart. Forget that. But after a year, each centimetre has gained 1 millimetre, so now it's an entire centimetre further apart than they were a year ago. And so on and so on. Sorry that I started counting from 1 and not 0. 1 and 2 are 1 centimetre apart, not 2 centimetre apart. 0 and 2 are 2 centimetres apart. I'm not editing that out. It's less than 100. You'll be fine. You can understand what I'm saying. Anyway, we call this Hubble's law. The fact that we get a straight line, we call that Hubble's law. The recessional velocity of a galaxy is proportional to the distance from us. Not always. There are galaxies that lie off this line, but that's because they're moving through space. So space may well be expanding, but if the galaxy is moving through space, then it's going to mess up our data a little bit. Andromeda, for example, the space between us and Andromeda, it's a nearby galaxy, that space is expanding, but Andromeda is still getting closer to us because even though the space is expanding, Andromeda is moving towards us faster than the space between us is expanding. Imagine I have a rubber band and 2 ants, and these 2 ants are deeply in love and want to be near each other, so they run towards each other. But I, being a horrible villain, grab the 2 ends of the rubber band and pull them apart. Now, if I pull the rubber band slowly apart, the 2 ants, if they start near each other and they're running, they might still be able to reach each other. But if they're far apart and opposite ends of the rubber band moving towards each other, then there's so much band in between expanding that the expansion of the band is faster than the speed the ants can walk towards each other. So even though they're walking towards each other, they move apart because the rubber band is expanding. The universe is expanding a bit like that. So that's the evidence, the redshift. And it's not just redshift. When you say what's the evidence for the expansion of the universe, redshift isn't enough. I have to say that it's the redshift of bodies that are farther from us, that redshift is greater. That's the evidence for an expanding universe, not just redshift. That's not enough detail. Because you get redshift if a galaxy is moving away from us. So if all the galaxies were moving away from us at the same speed, all galaxies would be redshifted. But they'd all be redshifted by the same amount. That's not what we see. We see farther galaxies, more redshift, therefore moving faster. Only explanation is space must be expanding. I'm hoping that that has clicked and you've got an idea of what's going on there. Lovely animations here. Don't know if that helps or not. So Expansion of the universe could be part of the Big Bang Theory, but that's not all, because you could have an expanding universe, but new universe appearing in the middle. And that would be a constant, steady density of universe. So that brings us nicely on to Lesson 101. Lesson 101 is the beginning, and it says the future. I'd love it to say the end of the universe. So the beginning of the universe. We've already met the idea that the universe is expanding, which is one of the pieces of evidence for what we call the Big Bang Theory, originally called the theory of the primordial atom. So the Big Bang Theory is the idea that the universe has expanded from a very high temperature, very dense state. 𝗟𝗶 wants you to learn that matter and time and space were created in the Big Bang. That's not quite what the Big Bang says, but that's what you need to learn. The Big Bang Theory does describe the expansion of the universe from a very hot, dense initial state. That's what it describes. But yeah, okay. So that's one piece of evidence, Hubble's law. That's one piece of evidence. There's another piece of evidence. If the universe was originally very, very hot and dense, and now it's not, then the universe being hotter should have been a brighter, a colour with a smaller wavelength. Okay, remember what we said? Stars that are hot, really hot, are blue. Stars that are a bit cooler, still hot, but cooler, are red. The higher up the spectrum of colours you go, the higher the temperature of the body. Well, if the universe was originally all of the matter of the universe in an incredibly hot, dense state, in a singularity right in the middle, maybe not a singularity, but right in the middle, really hot and dense state, then that must have been glowing incredibly brightly, and it must have been not just, blue light, not even X-rays, the tiny wavelength of electromagnetic radiation must have been emitted from, really high electromagnetic radiation emitted from that hot, dense body. Okay, so where is that radiation then? Well, the universe has been expanding, and because the universe has been expanding, that radiation has also been stretched out. All the space is expanding, so that radiation that's emitted by all bodies at a temperature above absolute zero, so therefore all bodies, which at the beginning of the universe must have been ridiculously high frequency, ridiculously low wavelength, by now, 13.7 billion years later, has all been stretched out as the universe is expanding. And when we do the calculations, we reckon it should be around about the microwave wavelengths of light by now. When we first started developing radar technology, and we got big radio telescopes in order to try to detect enemy aircraft in the Second World War, we discovered that there was this irritating hum, background noise from all directions in space that we could not get rid of. And as we have improved and improved and improved our technology, we have been able to map this radiation that we're detecting from all parts of space. Some places it's slightly brighter than others. It's only a tiny variation, but it's everywhere. And that is the cosmic microwave background radiation. Where it's slightly more dense, that looks like it's where it's slightly brighter, that looks like it's where the more galaxies are, where it's a little bit more dense matter, which kind of makes sense to us. But this cosmic microwave background radiation, CMBR, detected in all directions, is evidence for the Big Bang. Because if we had a steady state universe, where as the universe expanded, new universe was created in the middle, then the density of the universe would always be constant, and then we wouldn't have that cosmic microwave background radiation, the stretched out radiation that was emitted by the early universe when it was so hot and so dense. So the fact that we see this CMBR, this cosmic microwave background radiation, is another important piece of evidence for the Big Bang Theory. There are different models of the future. So that's the past, and we're pretty much settled on the past. Some really interesting physics happened. It didn't expand uniformly. There's a lot of stuff you can look up on this. The cause of the Big Bang is one of those things that's very, very difficult to describe. As matter gets more dense, we have to describe time as slowing down. So is there a starting point? And there's all sorts of very, very interesting, very, very difficult, even philosophical questions that the origin of the universe raises. We're not going to go into that in the GCSE physics. If you're interested, study physics and philosophy at university. You'll love it. But let's move on to the end of the universe. Now, it turns out that this graph, I'm going to go back one slide, this graph isn't quite right. It's only right nearby. 30 million parsecs, 30 megaparsecs, doesn't sound very nearby. If you open up a Google translator, a Google converter, and convert 30 million parsecs into meters, you'll see what I mean. It doesn't seem very nearby, but actually, if you get much farther galaxies, they're moving away from us even faster. Now, what that looks like is that the universe expansion isn't uniform, it's actually accelerating. The universe expansion is accelerating. Well, we didn't used to know that. We had to get much better telescopes to be able to detect the faint light from much more distant galaxies and then be able to do spectrometry on them to work out the redshift of those galaxies in order to be able to do those sorts of measurements to determine that the universe expansion is accelerating. So that's actually only in the last few decades, really, during my lifetime, easily during my lifetime, that we discovered that. It wasn't on my GCSE, I don't think. So this is really interesting. If the universe expansion is accelerating, then that eliminates various theories that used to exist, that I was taught when I was at school. One of the theories that I found quite a satisfying theory was the idea of the Big Crunch. So if here we've got the average distance between galaxies, basically it's the size of the universe, and on the x-axis, time, we are at 0, that's us now, and the gradient is there, okay, because we know the universe is expanding. It would be lovely, to me, if the universe wasn't actually 13.7 billion years old, the expansion wasn't uniform, and it went like this. Gravity pulling galaxies together, universe collapses again. Because then what we could have is another Big Bang after the Big Crunch, and then another one, and another one, and another one, and you'd have a cyclical universe. Now that is a philosophy that is very, very prevalent in Eastern religions, the idea of a cyclical universe. Unfortunately, the physics doesn't show that as being likely because of this accelerated expansion, at least not in the way that would be easily understood. Now, of course, you might have weird universe space-time topologies. If you trace a line over the surface of a donut, for example, you can get some really interesting things where it looks like you're moving away, but you're actually moving towards, and all the rest of it. So if you're interested in universe topologies that have an accelerated expanding universe but still have a big crunch, they do exist, but they are clutching at straws, I'm afraid. It'd be lovely. This is satisfying to my mind, but that doesn't make it reality. Might still be reality. In order for this to be true, we would have to have an awful lot of matter acting to pull everything back together, and the expansion of the universe would not have to not be accelerating. What we actually see is this here, with this dotted line that goes up here. This is what we are currently thinking is accurate. The black line here, this black arrow, this solid black arrow, shows a uniform acceleration of the universe, which was what was originally thought to be the case when Hubble's law was first written. So, what is it that determines which of these futures of the universe, the expansion out into oblivion, or the contraction of the universe back into a singularity? What is it that determines the future of the universe? It is the balance of dark matter and dark energy. Now, dark matter and dark energy are entirely different things. They just happen to have similar names. Dark matter, we've got a bit more knowledge about than dark energy. Dark matter is matter that does not interact with light, does not have any electric charge, it doesn't emit any radiation, it doesn't absorb any radiation. The only way we know it's there is because of the gravitational effect of that matter. We don't know what the matter is yet. We're trying to create it at places like CERN. We're trying to create it so we can investigate it, but it is found everywhere in the universe, and it does tend to clump around galaxies, so it interacts with gravity. We know it's there because we can see the effect of it. Just like we know the wind is there. We can't see it, but we can feel it. We can see the flags waving. Dark matter, we know it's there because of the way galaxies rotate. If we only had in the galaxy the matter that we can see, then they would not rotate in that way. The outer parts of the galaxy would be flung off into space. So we know the dark galaxy is there because of other effects like gravitational lensing, which takes us beyond GCSE level. We know this stuff is there. And if there's enough dark matter, then the gravity is that much stronger, then the universe could collapse down. But we know the universe's expansion is accelerating, which means that there is somehow energy being fed into the universe. We call this energy dark energy, and we know almost nothing about it. There are various fringe theories, alternative theories, like modified gravity theories to try to explain away dark energy, but they all fail when you compare them to observations. We're still working on it, okay? Physics isn't like a religion where we have a text and we say this is true, everything else is wrong. Physics is about observation and trying to write models that predict those observations to try and explain the nature of the universe. And where our models don't match our observations, we change our models. We don't say the observations might be wrong. We do have to double check them and triple check them, and that's why there's big teams of physicists. That's why everything gets peer reviewed. That's why there are multiple teams all around the world working on the same things. But we're not saying we know this is true and everything else is wrong. We're actually doing the opposite. Every theory we have, even the theories that we hold most I would say most sacred, but that's rubbish. The theories that we think are most correct, that's only because we have tried to prove them wrong for so many years. Quantum physics, we've tried to prove it wrong for over 100 years, and so far we've failed. That doesn't mean we think it's right, it's just the most right we've got at the moment, and we'll continue to try to prove it wrong. That's exactly what we did with Newtonian gravity. We tried to prove it wrong, and we successfully proved it wrong, which is why we now have general relativity, and we'll continue to try to prove that wrong. We know that general relativity and quantum mechanics are not compatible, so something is wrong. We just have to prove it and figure out what's wrong so we can improve it. That's what physics is all about. So dark matter and dark energy. This is the makeup of the universe as we can see it. Less than 4% of the universe consists of hydrogen and helium. And these aren't atoms. These are in stars, in galaxies. So these are the hydrogen-helium plasma. 23% of the universe's matter is dark matter. Just think about that. Okay, the Earth and the other planets and the asteroids and the comets and everything else is part of this thin slither, this thin yellow slither, along with all the other exoplanets and all the other matter out there in the universe that is not found in stars. All that matter that we can see is this thin yellow slither. And yet dark matter, which we know relatively little about, except how much of it there is, because we can detect it, but we don't know what it is, makes up nearly a quarter of the universe. Chemistry is concerned with this thin yellow slither. Physics is concerned with the rest. And dark energy, nearly 3/4 of the universe, and we know nothing about that. Nothing at all. Whew. Except an estimate of how much there is based on observations of the accelerated expansion of the universe and models that predict that we must have about whatever these arbitrary units are. I mean, this is really interesting stuff. You know that joke, don't trust atoms, they make up everything. I really don't like that joke, because atoms really don't make up everything. 73% of the universe is dark energy. That's not atoms. Because atoms, well, it's not atoms. 23% is dark matter. That's not atoms. Atoms interact with light. Dark matter doesn't. 4%, just a little bit less than 4%, is hydrogen and helium found in stars. They're not atoms. They're ions, because it's a plasma. So the atoms that make up the universe is this tiny little yellow slither. Don't trust atoms. They make up everything. No, they don't. They barely make up anything. And chemists get all excited about that little slither. Anyway, I'll leave that. So this is where I will stop. That is the end of lesson 101. The future of the universe is bleak. The universe will continue to expand until all the matter is so spread out that nothing can happen. A cold, dead universe for all eternity. And if you've enjoyed this video series, don't forget there's the GCSE astronomy video series, where we go into the space stuff in much, much, much more detail. A whole GCSE just for space. It's a good course, 16 videos worth. If you want to look at particle physics in more detail, I've got a whole video series on particle physics. Maybe you're about to start A-level, because you've been revising using this video series for your GCSE exams. Well, then I've got a GCSE to A-level physics transition course you can look at. Maybe you want to have a look at some practical work at A-level. I've got all sorts of videos all over the place. So just see what's on my channel. And if you want to take part in live tuition, not like this video, live interactive tuition, there's the QR code. Go there, physicswithkeith.com. Join up with the online tuition sessions. Participate, improve, succeed, and share. Thank you very much for tuning in. I hope you found it useful. Share it with your friends.